Hello, and welcome to my presentation on the Computational Lab of Week 3. In this presentation, I will be discussing and explaining the problems faced in this lab and the computational methods employed to solve these said problems. This lab required the use of density functional theory, or DFT, and molecular dynamics to solve such problems. And to go straight into things, the first problem given required explanation behind which of the two molecules given below here had the greater ability to act as the electron transfer layer, or ETL, and which had the greater ability to act as the hole transfer layer, HTL, in an OLED design. DFT was utilized to solve this issue. And so, to firstly explain the theory behind this problem, we see our structure of our OLED design and the two molecules of interest below it. For our OLED to work and create the emission of light, we firstly notice that we have a cathode which transports negative charge, or electrons, and an anode that transports positive holes. In order for this emission of light to occur then, the electron and the positive hole have to meet in the so-called emission layer, or EML. Here it is. And not worrying too much about our electron injection layer, EIL, or hole injection layer, HIL, it must be such that for our molecule to behave as an ETL, it must have a LUMO energy low enough for our electron to transition from the EIL to the ETL. The HOMO of this though must be low enough in energy so that when our positive hole makes a transition to the EML via the HTL, the positive hole will not be able to transition further to the ETL and thus escape the EML. In light of a good HTL then, it must be such that it has a high enough energy HOMO for our positive hole to make the transition from the HIL to the HTL, but a high enough energy LUMO so that it prevents the electron that has transitioned to the EML from the ETL from transitioning further to the HTL. Now these two, should we say boundary conditions, make it such that it's now much more likely our positive hole and electron will find each other in the EML, as they are now forced to stay within it after their various transitions. Therefore then, to solve our problem, we must calculate the HOMO and LUMO energies of our two molecules to deduce which can act as the HTL and which can act as the ETL. So, to do this, I utilised the following method. I firstly launched the Orca tool on nanohub.org. Once the tool had launched, I was then brought to the basic input page, and from there I set my task to geometry optimization, made sure that I had set up the molecule to hydrogen, so there it is in red, and also made sure that the advanced options option was set to yes. Now on the next step, it will be possible to see that it wouldn't really matter which molecule I had chosen to base the optimization on, so in this case hydrogen, as I will be changing the molecule and thus coordinates of the system anyway. From there, I went to the geometry input section, so you can see it at the top right here. This is where I set my coordinate choice to Cartesian, so here it is, and went to input then my chosen molecule's coordinates. Now to do this, I right-clicked on the atomic structure box and selected Upload. From here then, I then chose one of the molecular coordinate files associated with one of the molecules of interest with this given multiplicity, and clicked the Upload button to upload the coordinates to the program. So, as you can see, all of the coordinates for my molecule of choice were now in the program. I also made sure that there were no extra numbers within the file. For instance, when I uploaded my file, there was a given 2-digit number in this circled region by here. It was important to get rid of this to ensure my simulation ran successfully. You will also note how I mentioned the multiplicity just a second ago. This had to align with the coordinate system that my molecule had at the time. So in this case, my molecule's coordinates are for the singlet multiplicity, so I had to make sure that my multiplicity was of a value of 1 to fit in with this, as you can see here in the red. Moving then on to the energy expression section, I made sure my method was set to density functional theory, my XC potential was set to B3 LYP, and my basis set was set to 631G. Although it was important in my case to make sure that my geometry wasn't optimized, as the coordinates of the molecule I imported into the program had the molecular geometry already optimized. Taking this step ensured my simulation did not take too long to run. I then went ahead and performed the simulation, as there were no other parameters to change. To retrieve the data then necessary to determine the stability of the specific multiplicity state of the molecule, I went to the output log under the results section of the simulation and searched for the total energy within the log. From there, it was then important to determine the total energy of the molecule, so circled by here in red, to then compare this value to its triplet counterpart to determine which one was the most stable state for the molecule to exist in. So, as a reference point, we can see the molecules of interest in the bottom right-hand corner here. And as I just mentioned, to determine the most stable state of the molecule, it was important to make direct comparison between both the triplet and singlet states of each molecule in terms of their total energy. The molecular state that is most stable is the one that has the greatest negative value associated with itself in terms of its total energy. And so, what can be seen is by running through their various total energy values, both of our molecules are going to be most stable in their singlet states. So now we can move on to determining which molecule has the potential to act as either a HDL or ETL in our OLED. Remember, to do this we need the HOMO and LUMO energies of our molecules. In comparison to before, when I determined the total energy of the molecule, I did search for total energy in the find section, but instead I now search for orbital energies in that search box in the output log section again. I then scroll to the HOMO orbital. So this is the final orbital that has its occupancy of 2, as you can see, and then the LUMO follows this below with its occupancy of 0. Their associated energy values are then given in electron volts, circled in red right here. And so, laying all of this information out on one slide, what can be seen is that in regards to our PA molecule on the left here, it has both the highest energy HOMO and LUMO, whilst the PB has the lowest values of these. Going back to our HTL and ETL definitions then, it must be such that our PA compound will be a worthy HTL layer compound, as its higher energy HOMO will allow for easy positive hole transfer to the EML, whilst its higher energy LUMO will then prevent the electrons transitioning from the EML to the HTL once they have transitioned from the ETL to the EML. Our PB compound will thus be our ETL compound, as its lower energy HOMO will prevent the transfer of the positive hole from the EML into the ETL once the hole is in the EML, and its lower energy LUMO will allow for easy electron transfer from itself to the EML. Now lastly, this exercise required the calculations of both the ionization energies and electron affinities of our most stable molecules, so in this case the singlet state of our molecules. So, starting with ionization energies, remember that this is the energy required to remove an electron from a molecule or an atom. And so, to do this, we're going to have to go back to where I defined how to obtain the orbital energies of the molecules. All we have to do to determine the ionization energy values of the molecules is to pick out the energy of the HOMO orbital of our neutral molecule, and thus say that we need the positive equivalent in energy of this HOMO to ionize the molecule. So, in the case of our PA compound, what we're going to see is that its HOMO is of a value of minus 4.6219 electron volts. So therefore its ionization energy must be of a value of 4.6219 electron volts. In terms of our PB compound, the ionization energy can then be calculated to be 6.1065 electron volts. And as for some context, here I have then shown the HOMO orbitals of the two molecules studied in this exercise, both of which modelled on VMD. In terms of our electron affinities then, the calculations for this are a bit different. Remember that the electron affinity is defined as the energy released when an electron is added to an atom/molecule. To then start the calculations of the electron affinities of our molecules, what we have to do is upload the coordinate file of our molecule in the anionic state. But we also have to change its multiplicity to a value of 2 now, because we are no longer dealing with our system having all paired electrons. Once we have done this, the charge of the molecule must then be changed to -1 this time to add in the extra electron into our system so that we fulfill the molecule's anionic status. Then we work out the total energy of our molecule like we have done so before. So remember that this can be searched for in the simulation results, and this would be equivalent to the energy of the molecule once it has gained an electron. So there it is. We will do the same thing then for the other molecules too. Once this step is done, the next thing to do is directly compare these anionic energies with the total energies of the neutral molecules. It is known that our electroaffinity is the energy released upon adding an electron to our atom/molecule, as I've said before. So, to calculate our electroaffinity, this can be done so by taking the total energy of the anionic molecule away from that of the total energy of the neutral molecule. Now do remember that the total energy of our neutral molecule is the total energy of our neutral molecule in that singlet multiplicity state, i.e. the most stable state of that molecule to exist within. So, in the case of our Pa compound then, what we're going to see is that its electron affinity can be calculated to be a value minus 1.29014 electron volts, whereas in our Pb compound, this can be calculated to be of a value minus 0.53517 electron volts. And again, for a bit of context, I have shown the lumos of both of these molecules, and these are the orbitals in which the electron will be being added to in the case of the first electron affinity of these molecules taking place. And this concludes the solution to the first exercise in this lab. And so the second exercise in this lab was to look at how a single alpha helical segment of the 2b part of the Vimentin intermediate filament dimer will perform under a given force. The structure of this segment is shown below right here. Now, upon the force being applied in this case, it will cause the alpha helical structure to stretch and induce its unfolding. This simulation will allow for determination of how well this particular filament reacts to such a force being applied, and how well the structure can retain its fundamental shape. We'll be using a simulation to look at this, and these simulations are going to be of the SMD type, and this is where a force is applied to the alpha helical segment in this case, which will simulate its deformation evolution over a given number of steps at a certain velocity of occurrence. These simulations will be utilizing molecular dynamics, and to show you how I perform the simulations, I have a series of images. So, the first step is to go to the Stretch Mold tool on nanohub.org and launch it. So, once the tool launched, the first page shown was the initial geometry page. Here it was necessary that I put in all of the necessary files for the simulation, but making sure that the fixed atoms box was set to yes. So there is your fixed atoms box. Once this was done, on the SMD parameters page, again, the necessary file was deposited along with setting the simulation to use the steered molecular dynamics simulation style. Within this setting, it was then appropriate to set the velocity to a given value. In this case, I used the conditions required for the task 2 simulation, whereby the velocity was 0.05. In addition to this, it was because the protein structure used in this lab was orientated along the x-axis, the force being applied to the protein therefore should have been along this axis too. Thus, I gave the direction x box a value of 1, the others being a 0 value to direct this. Next up then, in the simulation parameters section, I set the number of steps to the defined value in task 2, which was 5,000. The simulation was then run. There was no need to change any other parameters in the settings. Now once the simulation had finished, I then proceeded to the VMD movie files zip section under the results tab and downloaded the available data using this little icon by here. VMD was then opened. To input the molecule into the program, I went to the main window in VMD and then proceeded to File, then New Molecule. From there, I went to Browse to obtain the correct file. In this case, this was in the recently downloaded zip file from the Stretch Mold program. From there, the PSF file, so there's your PSF file, was then loaded into the program. So now we should get this in our main window in VMD because our molecule has now been imported into the program. Now, from this point, it was then appropriate to load in the extra data into our molecule that allows for the simulation to take place. So to do this, I clicked on the recently added molecule right by here to highlight it in green. So to load this data in, okay, we're going to pop back up here for step number 10. I headed into the File section, but now I clicked on the Load Data into Molecule tab. Then the next thing that I did was again browse the zip file and picked out the DCD file and loaded that into the molecule. Now, the protein structure that was shown wasn't really well defined in terms of its structure. I mean, you can see the fact that there is a polypeptide chain here, but you can't massively work out what the secondary structure is. So, to show the protein segment in a clearer light, I then went to the VMD main window, highlighted the molecule like before, so there it is in green, and from there I went to the graphics tab and then the representation section. From here I then created a new representation for the protein by clicking on the Create Rep button. So in this new representation I selected my colouring method to be secondary structure and my drawing method to be new cartoon. This allowed for my protein's secondary structure to be clearly visible and surrounded by the water particles that were there prior to the new representation being added. To then play out the created simulation, I headed back to the VMD main window, found the play button, circled right by here, and then visualized the simulation from there. Now, there were 3 simulations I performed, and the one I am going to play out of the 3 is the one I have given the method for to create in this video. So 5,000 steps with a velocity of 0.05. So to try and answer the final part of this exercise in regards to what the simulation is showing us, it appears that with the water molecules, they start to congregate around the area of the protein that starts to unravel to try and perhaps stabilize the structure as much as possible. This can be seen a bit better in this second simulation here, over 10,000 steps this time. So you can see how the water molecules start to congregate around that unraveling structure of the protein there. And this could be due to how the protein is losing the hydrogen bond interactions between the amino acid residues in the alpha helices as a consequence of this deformation. But as more of the protein structure starts to unravel though, the water particles may not be able to spread out as much to stabilize the whole structure anymore, and so they start to concentrate on one particular region to try and stabilize it as much as possible. The degree of stabilization in this case may be greater than if the water molecules were more spaced out, due to a lack of hydrogen bonding between both the water molecules and the protein structure in this case. This therefore concludes the solution to exercise 2 in this lab, and thus concludes this presentation. Thank you for watching.